So welcome everyone. Welcome to today's session. And today I am going to discuss GATE 2024, all the quantum mechanics problems. So the quantum mechanics problem, as you will see, that basically in GATE are divided into four categories: basics of quantum mechanics in one dimension. That contains many topics like potential well, harmonic oscillator, barrier potential, and so on. Then we have quantum mechanics in three dimension, which is hydrogen atom, angular momentum, and then perturbation theory. So the paper was very much easy on. I feel that in 2024 the paper in terms of quantum mechanics was easy paper, and no question would need more than 2 minutes to solve. So it was straightforward calculations. Yeah, in one or two questions there were some tricks which were involved, or the very fundamental concepts were involved. Okay, so let's begin. And today's session is going to be very important for IIT JAM aspirants and JEST aspirants as well, because I found the question were very similar to your examinations as well. Okay, so let's see. So the first problem was actually from basics of quantum mechanics. So by looking at the diagram or the question, what you can see is it is infinite one dimension potential well is given. So the system we have is a one dimensional infinite well, and the wave function is given. So wave function is a superposition wave function. So your wave function is in superposition of three states: phi 1, phi 2, and phi 3. As you know, in quantum mechanics, your system can be in the three different states at the same time. And that is what is happening here. It is in the three different states: phi 1, phi 2, phi 3. And when you will do the measurement, you will find your system in any one of the states. Okay? And you can find the probability that what is the probability that you will get the system in first state, what is the probability to get in second state, and what is the probability to get in third state. Anyway, that is okay. Okay, clear. Now the next thing is phi 1, phi 2, phi 3 are the normalized ground state. So this is your ground state, this is your first excited state, and this is your second excited state. So for this n is equals to 1, for this n is equals to 2, and for this n is equals to 3, right? That is given. And E1, E2, E3 are the energies eigenvalues, and phi 1, phi 2, phi 3 are the eigenfunctions. Very simple. What is an expectation value of the energy of this particle? So you need to find an expectation value of the energy. In the yesterday's lecture, when we discussed CSIR Net PYQs, we talked about the expectation values, and expectation value can be found using this formula. This is the expectation value. So you can write using phi, the operator. So the operator of energy is Hamiltonian. So the operator of energy is Hamiltonian. So that is why I have written H cap and then again phi. Okay. So let's put the values. We are already knowing the values. So I am putting the value of wave function. So this is my wave function. So if you have symbol like this is known as ket, and ket means you write your wave function as such. But if you have a symbol like this, it means bra, and bra means you have to do the complex conjugate. So first I have to do the bra. So let's do the complex conjugate of my wave function. So root 2 by 3 is a real number, so that will remain as such. But e ki power iota is not a real number, so you have to convert iota into minus iota. Or so here you already have a negative sign, so this will become plus, as you can see here. And phi 1 will become phi 1 star. Basically what you're doing is doing complex conjugate. So phi 1 becomes a phi 1 star. Okay. Then the second term, 1 by root 6 remains 1 by root 6. E ki power iota pi by 6. So here you see iota will become minus iota. So you can see minus iota pi by 6. And here you see plus iota e2 t by h cut. And then phi 2 star. And then the third term 1 by root 6 remain as such. And here you see iota will convert into minus iota. So that is again what I have done. And then phi 3 star. And then in middle you have h cap. Okay, I have h cap here. And then I have to write my wave function as such. So here I have just written my wave function directly, not changing anything, just written my wave function directly from there to here. So this much is okay. And the student who already know how to solve this question will understand by now how unnecessary these steps are, right? If you can do this mathematics in your mind itself, right? Yes, everything has to be written inside integration. Okay. Yes, this everything is under integration, right? Yeah. So because we are not following the Ket-Bra notations. So if you are following Ket-Bra notations, then it is okay, then you don't have to write integration. But if you are using the wave function approach, then you have to write integration. Okay, but that does not matter. Chali, anyway, now this h cut will act on this, so this operator will act on this. So this h cut will operate on phi1, then this h cut will operate on phi2, and this h cut will operate on phi3. So when h cut operates on phi1, what happens? So let's say you are in state phi1, and h cut operates means your operate means, what does the meaning of operate? So what is the meaning of h cut operate? H cut operate means you are measuring energy. So you are trying to measure is energy. So when H cut operates on state 1, what is the energy that you will get? Okay? What is the energy that you get? Then in that case, you say E1 into phi1. So you will get energy E1. So someone asked that why there is no need for integration if you have a Cat-Bragg notation. So it's a very fundamental question. So I hope you should know this. It's not about integration or not integration. It is about the fundamental concept of writing the quantum mechanics. So in quantum mechanics, you have three kind of notations. One is function approach. So you have wave function, phi1. You have Cat-Bragg operate. So this is your cat, right? This is known as a Dirac notation, or you can even write it as a matrix form. Okay. So currently we are using this. Okay. So what is the meaning of dot product? How do you write dot product in different situations? In this, you write a dot product like this. So let's say I'm doing the dot product of phi1 and phi1. So this is a symbol. That's it. That's a symbol. But in this, how do you write a dot product? In this, you write a dot product using phi1 star into phi1 into dx. That is a method of writing the dot product in function approach. And if you're doing in matrix approach, then you will have one row matrix and one column matrix, and then you have to multiply them. Okay. So this is a three different ways of writing the inner product. So if you're using the function approach, like for example, you're saying you're using the wave function approach. You have some wave function under root 2 by pi sine n pi x by L. In that case, you have to do things like this. In that case, inner product is given by this. But if you have a Cat-Bragg notation, then this is your notation for an inner product. It is phi1 phi. And if you have a matrix approach, then basically you have to multiply one row vector with one column vector. So this is the fundamentals of quantum mechanics. Okay? So here we are basically dealing with these symbols are directly given to us, right? In you can see here, these symbols are more or less are sort of given to us, right? I can write this as like this. Okay? So that is why I have not given the integration symbols as such. That is why I have not shown the integration symbols. I can just call it as like this. I can use it in a Dirac notation, and I can just work with my notations as such. Okay. Okay. So where I was, trying to say that what will happen if H cut operates on phi1. If H cut operates on phi1, H cut operates means you are measuring the energy, and in which state your system is. Your system is in state phi1. So if your system is in state phi1 and you are measuring the energy, you will get the energy value E1, and your system will still remain in state phi1. Similarly, if you are in state phi2 and then you are measuring energy, basically you are operating H cut. In that case, you will get energy E2 and you will remain in the system state phi2. If you are in state phi3 and then you are operating H cut, then you will get energy E3 and you will remain in the system or a state phi3. Okay? For one-dimensional well, we know the formula for energies. So the formula for energy eigenvalue for one-dimensional well is n square pi square h cut square by 2ma square. I hope that this formula everyone remembers. This is a BSc level formula, IIT JAM formula situation. So if you put n1, you will get pi square h cut square 2ma square. So this is energy E1. If you put n2, you will get 4 times of this energy because 2 ka square is 4. So E2 is actually 4 E1. And if you put 3, you will basically get 9 E1. Okay. So when this H cut will operate here, you will get value E1 into phi1. But when this H cut will operate here, you will get 4 E1 into phi2. And when this H cut will operate here, you will get 9E1 into phi 3. Basically, you're getting E2 phi 2, E3 phi 3, but E2 is 4 times E1 and E3 is 9 times E1. That is a concept I'm using. Once that is done, then I have to multiply left hand side and right hand side. And you already know that if phi 1 star and phi 1 are inner product, if the inner product of phi 1 star and phi 1 happens, then it is 1. But if the inner product of phi 1 star and phi 2 happens, basically what is phi 1 star and what is phi 1? This is basically can be written as this. But how can you write this? This is written as phi 2 into phi 1. So basically the inner product of the same wave functions is 1, but the inner product of two different wave functions is going to be 0. That is why only 3 terms will exist. Phi 1 star phi 1, phi 2 star phi 2, and phi 3 star phi 3. All the cross terms will go to 0 because phi 1 star into phi 2 will be 0, phi 1 star into phi 3 will be 0, phi 2 star into phi 1 will be 0, phi 2 star into phi 2 will exist, phi 2 star into phi 3 will be 0. So that is what is going to happen. And that we discussed in detail when we discussed the CSIR Net PYQs yesterday. Okay? So only 3 terms will exist. So if I multiply this first term with this first term, you see iota and iota will cancel and it will become 1 because e ki power plus and e ki power minus will give e ki power 0 and e ki power 0 is 1. Gone. Under root 2 by 3 and under root 2 by 3 will give me 2 by 3. Okay? So that you can see I am getting 2 by 3. And why you are getting this even? Because you see when H cut operated on this, you got E1 into phi 1 and that E1 you are getting here. That E1 you are seeing here. Perfect. Then similarly, we are doing phi 2 star phi 2 multiplication. So when I multiply second term with second term, 1 by root 6 and 1 by root 6 will become 1 by 6. Exponential terms will just cancel and it will become e ki power 0, 1. And then phi 2 star and phi 2 will give me 1. But you have 4 E1 here. Okay. So similarly, I'm getting 4 E1. Okay. So here I'm getting 4 E1. So basically I'm getting E2, but E2 is 4 E1. Similarly, in the third term again, 1 by root 6 and 1 by root 6 will become 6. Exponential term will cancel out because e ki power plus and e ki power minus is e ki power 0. E ki power 0 is 1. And then I get E3 and E3 is nothing but 9. Now I can just add them together. So I will get 17 by 6 E1, which is your option number A. Okay. So that was your question, and any doubt in this one, you will let me know. So if you do basic assignment, which I shared today, IIT JAM quantum mechanics topic wise questions, this is a very fundamental question. And I hope that everyone knows how to solve it. And once you know the practice, I mean, you don't have to do this much mathematics. Don't think that it is, so it is just to show you I have written so many steps. But to be honest, this question could be done in one, not even by picking up the pen. You can easily do this. So what I have actually done is nothing. I have just, what I have done is squared this up. So I get 2 by 3 into E1 plus square this up. I get 1 by 6 into E2. And then square this up. I get 1 by 6 into E3. Okay. And then I just use the simple logic that E2 is nothing but 4 E1. And then I use a simple logic that E3 is nothing but 9 E1. And then if you solve this up, you will get 17 by 6 E1. That's all. That was only 3-step question. Okay. And why this thing works is basically what I proved you. Why this is working out. Clear? So any doubt, anyone, please let me know in this question. Yeah. So question 2 is very interesting in two contexts. Number one, it is basically a very general theory of quantum mechanics. And second, it tells you about how to understand the wave function diagrams. So again, a very simple question. I think that if you know a very basic concept, you can solve this out. And if you have watched my lecture, more or less nothing is outside there. So if you see Vx, potential is given. So potential is given and they're saying that potential is infinite if x is less than 0. So basically this is your x-axis, and if x is less than 0, potential is infinite. So your wave function cannot be there, or your particle cannot be there where the potential is infinite. So if you are at a position where potential is infinite, it means you have infinite energy. So that is not possible. You cannot have infinite energy. So at this position, wave function is 0. wave function must be 0 at x equals to 0. Okay, so at x equals to 0, wave function should be 0, because you see at x less than 0, wave function is 0, and wave function is always continuous. It is always continuous. So if wave function is 0 at x less than 0, then wave function will be 0 at x equals to 0 as well, at the boundary also. So at the boundary also, the wave function must be 0. Okay, so that is a continuity condition. So first of all, we should see that which option cannot be true. So D option cannot be true, because at x equals to 0, your wave function is not 0. Your wave function is something else, and that cannot be possible. Okay? Otherwise, if this diagram is true, then what is happening? On the left hand side of the boundary, wave function is 0, but on the right hand side of the boundary, wave function is not 0. So at the boundary, wave function is discontinuous, because if you are approaching the boundary from this side, wave function is 0. But if you're approaching the boundary from this side, wave function is not 0. So at boundary, wave function becomes discontinuous, and your wave function can never be discontinuous in this universe. Okay? But if you look at the other diagrams, for example, diagram number A, if you approach from here, wave function is 0. And if you're approaching from here, then also the wave function is going to 0. So from both sides, wave function is 0. So that is why other three options can be true, but option number D cannot be true. Okay. So this even first line suggests the option D is wrong. Then potential is 0 everywhere else, and potential is basically V naught when A is, your x is from A to B. So this is your diagram. So when your x is from A to B, your potential is V naught, and everywhere else your potential is 0. Very nice. The two kind of wave functions you are seeing in your diagram. One kind of wave function that you are seeing is oscillating wave functions. You see the oscillations, sine, cosine wave. And the second kind of wave function you see is a decaying wave function. You see decay. The wave function is decaying. So when the wave function should decay and when the wave function should oscillate, that concept should be clear. In what region my wave function should oscillate and in what region my wave function should decay, because only these two categories we are seeing. And that comes from the Schrodinger equation. So our Schrodinger equation is minus h cut square by 2m d square phi by dx square plus v phi equals to e phi. This is the basic Schrodinger equation. I hope everyone knows this. If I take this term on other side, I will get d square phi by dx square minus 2m by h cut square e minus v into phi. Now the two cases will come. In one case, this e minus v will be positive, and in second case, this e minus v will be negative. If e minus v is positive, it means e is greater than v, and if e minus v is negative, it means e is less than v. So let's understand both the cases. If e is greater than v, which basically means e minus v is positive, so this entire thing is positive. So we can call this entire thing as alpha square, some alpha square, and your Schrodinger equation will become d square phi by dx square equals to minus alpha square phi. Okay, so this entire thing is positive, so this negative sign remains as such. Okay, so this is your simple harmonic motion. This equation resembles with simple harmonic equation. Okay, and if you solve this equation out, you will get sine alpha x and cos alpha x as a solution, basically a wave solution or basically a oscillating solution. So whenever your energy is greater than the potential, in that case, E is greater than V, the solution should be wave. It should be oscillating. On the other hand, if your energy is less than V, so if this thing itself is negative, then this negative and negative should become positive. Okay, so let's make it positive. So if I make this negative positive, so how can I make this positive? So I can just take negative common. So I will get 2m by h cut square v minus e into phi. And here we have d square phi by dx. Now this entire thing is positive. Okay, na? So because I'm assuming in the second case that v is greater than e or e is less than v. So now this is positive. Okay, so that is why I take a negative sign common here, so that I can, otherwise what will happen is I might think that this thing is negative, but you see what is happening. If V is greater than E, then overall this thing itself is negative. But I cannot see that from my eyes. I might get a misconception. So that is why I took the negative common, so that this negative do become positive, and I can clearly see that, okay, this here I have a positive, and I will have this positive for rest of my life, because this is never going to be negative now. Okay, so nothing I have done, just in first case I have written the thing as such, but in the second case I just prefer to take negative common. That's all. So then whatever is left, I can call this as beta square, and then my Schrodinger equation will become d square phi by dx square equals to beta square phi. Okay, now at least 2-3 times we have discussed this in many times. This is now again a hyperbolic solution. So the solution to this equation will be hyperbolic, because there is no negative sign here. If there is a negative sign here, then you have a wave solution, sine and cosine solution. But if you have no negative sign here, then you have a solution something like this: a की power e की power minus beta x plus b into e की power beta x. Or you can even write this as sine hyperbolic or cos hyperbolic. So basically the solution that you get is decaying. So the two things that we learn: if our energy is greater than V, then we have a wave solution. But if our energy is less than V, then we have a decaying solution. And that is always the fundamentally the true thing for quantum mechanics. Now let's see what is given to us. It is given that E is less than V. It is given to us. So if E is less than V, it means we should have a decaying solution. When we should have a decaying solution? Here we should have decaying solution, because V only exists here. V is not anywhere else. V only exists here. So here we should have a decaying solution. So if you look at the option A, it is not decaying. You see, it increases and then decreases. So it is not a decaying. So this is wrong. Okay, this is anyway gone. And here also this is also wrong, because you see here you don't have a decaying solution. Here you have is a oscillating solution. So this is also wrong. So the only option which is correct is this B. Why? Because you see here you have a perfect decaying solution. Your wave function is 0 at 0, and once you cross this, you have an oscillating solution. Okay, so that is what we have. So we have oscillating solution there, we have a decaying solution in between, and our wave function is 0 at 0. So all the three conditions are being satisfied. So that is why option number B comes out to be true. Okay, sir, why not 4? Because you see wave function is not 0 at 0. Wave function must be 0 at 0. Why? Because here you have infinite potential. So wave function cannot be here. So if the left hand side wave function is 0, then at the boundary also the wave function should be 0. Otherwise wave function will not be continuous. Okay, so that is why at x equals to 0, wave function should be 0, which is not the case in D. That is why D is wrong. Okay, and that is why the B is the correct option. So we do three concepts. At x equals to 0, wave function is 0. Perfect. Then if our energy is greater than potential, then we have an oscillating solution. But if our energy is less than V naught, which is the case here, then we have a decaying solution. So we should have decaying solution here, and we should have oscillating solution here. Okay, so let's say, for example, let's say this potential is 5 and our energy is 2. So in this region, energy is less than V, so decaying. But in this region, V is 0, right? V is 0 and 2 is greater than 0, right? In this region, E is greater than V, so we should have oscillating solution. Okay, so that is why you see the graph number B to be exactly correct. Yes, please. Any doubt in this question? Very important, very fundamentally very important question. Then we go for the third question, and very easy again. So they are saying that the wave function for a particle is given. So they are giving you the wave function, and then they are asking what will be the potential. Wave function is given, you have to have guessed the potential. So nothing as such. You have Schrodinger wave equation. So I am writing my Schrodinger wave equation. That's all. And then I take my wave function, and then I take the double derivative of it, just to compare with my equation. So if I take the double derivative, you just do the double derivative of this, you will get minus iota alpha square into e की power minus iota alpha x plus beta. This can be written as minus alpha square because iota square is -1 and alpha is alpha square, right? And this thing can be written as phi. So basically what do I get is that d square phi by dx square equals to minus alpha square x. Okay. Now, if you carefully see, if I call this thing as E, if I take this thing as E, just for a minute, assume that because this is a constant and total energy is also constant. So minus alpha square, let's say, is E, then basically what you are getting is d square phi by dx square equals to E. Okay. And that will only be true if this term is 0. Basically, d square phi by dx square is equals to some E into phi will be true only if this term is 0. It means that this equation itself is showing yet potential is 0, option number C. Okay. So anyway, this is for the free particle, right? What is happening is I took the wave function. So one equation I'm trying to make, and I'm trying to compare my equation with the Schrodinger equation. So this is my Schrodinger equation. I'm not using it. I'm just trying to compare with it. So I take the wave function. If I take the double derivative of this wave function, I will get minus alpha square phi. So this is my equation that I have. This is my equation that I have. Okay. So now let's see. Option D will be correct. Your wave function will be sine alpha x, but not the potential itself. Your wave functions will be sine alpha x, not your potential as such, right? So potential is not oscillating, wave function is oscillating. That's a very big difference, right? So okay. So you get this equation. This is your equation. If you compare with your Schrodinger equation, when will this equation be true? This equation will be true if you make this equals to 0, and then you can clearly see that your d square phi by dx square will be directly proportional to phi, as you have in this case. D square phi by dx square is directly proportional to phi, right? But let's say your potential is not 0, it is alpha square x square. Then you can clearly see that your d square phi by dx square is not directly proportional to phi. It is then you have to take this term on other side, and then it will be proportional to 1 minus alpha square x square, or 1 minus e की power minus ax, or 1 minus sine alpha x. But nothing like that is happening. Your d square phi by dx square is directly proportional to phi. That's it. And that will be true only if this goes to 0. In that case, d square phi by dx square is directly proportional to phi. And you can bring this term on other side. That is anyway constant, does not matter. Okay. So if I actually put this v0, let's put this v0. What is an equation that you will get? You will get d square phi by dx square equals to minus 2me by h cut square into phi. And then I can just call this entire thing as alpha square. Right. In my equation, this is alpha square. In Schrodinger equation, this is this. Okay. So basically, alpha square can be written as 2me by h cut square. That's all. Just a comparison, but they're not asking what is alpha, but just a comparison. Okay. So basically, what we are getting and what Schrodinger equation we have, if we have to match them together, both of them will match only if potential is 0. Because if potential goes to 0, your double derivative is directly proportional to phi. And that is exactly what we are getting. Exactly what we are getting. Okay? Always remember, this is an equation for a simple harmonic wave, simple harmonic motion. This is a wave function of a simple harmonic function. And simple harmonic functions in quantum mechanics are obtained when potential is 0 or constant, and your energy is greater than potential. If your potentials are doing some zigzag motions like this or this or this, then you cannot have perfect oscillating solutions as we are having here. Okay. So in order to match our wave, our equation with the Schrodinger equation, potential must goes to 0. And that is why option number C is correct in this case. Clear? So it was just a very simple match. It just have to click. Okay, yeah, this is what I have to do to match both. Yes, it was a hit and trial question. There was Some people can also do this with variational principle, but that will be very long process and there is no need. That we use for a tough questions. Okay? Yeah. Any doubt here? So fourth question was, I think, one of the difficult problems, because not every student can understand, because it was very simple actually. When I saw the question once and I realized, okay, how they are tricking the students. So it was a trick question, but it was easy one. Easy trick was there. Okay, so let's see what was the trick. So there were two tricks involved. Number one, it was a multiple select. So anyway, we can have more than one correct option. And the question is from harmonic oscillator. How do I know? Because potential is half m omega square x square. So if you have potential equals to half m omega square x square, then it is a harmonic oscillator. But we are also adding some constant value to it. So that is okay. We can add constants and it will overall increase the energy. Nothing else will happen. It will just overall increase the energy. Okay. The trick which was there is this. It is a half harmonic oscillator. It is harmonic oscillator only when x is greater than 0. But if x is less than 0, then it is infinite. So it is not full harmonic oscillator. It is just a half harmonic oscillator. So on the left hand side, potential is infinite. If potential is infinite, then wave function is 0. And if the wave function is 0 on left hand side, then wave function must be 0 at as well, on this boundary as well. So wave function should be 0 on the boundary. That is why you cannot have this state, this state, this state, this state. Why? Because these are the wave functions of harmonic oscillator. I just gave this diagram for a reference purpose. These are the wave functions for a harmonic oscillator. If you look at n equals to 0, you see that your wave function is not 0 at boundary. That is why you cannot have this wave function in half harmonic oscillator. In full harmonic oscillator, this wave function is okay. This is acceptable. But in half harmonic oscillator means one side is harmonic oscillator, but other side is infinite potential. So you cannot have any wave function on this side. If you cannot have any wave function on this side, you cannot have any wave function on the boundary as well. Otherwise, discontinuity will be there. So wave function will be 0 at x equals to 0 as well. So that is why this cannot be true. So n equals to 0 is not a possible value. Similarly, n equals to 2 also, you see here, but n equals to 1 can exist, because for n equals to 1 at x equals to 0, you are getting perfect 0. You see how perfectly 0 you are getting here. So this is acceptable. N equals to 1 is acceptable. N equals to 2 is again not acceptable, because you see you are not getting 0 when you are at x equals to 0. So again, n equals to 2 is not acceptable. 3 is perfectly acceptable, because you see at the center you are getting perfect 0. So 3 is also acceptable. So n equals to 1, 3, 5, 7 are acceptable. 2, 4, 6, 0 are not acceptable. That is what happens if you go from full harmonic oscillator to half harmonic oscillator. So my energy values, so my ground state value. So first of all, what is the energy values in harmonic oscillator? It is n plus half h cut omega. I hope you know this. You have watched the lecture of harmonic oscillator. You know the energy eigenvalue of harmonic oscillator is n plus half h cut omega. If you want to know ground state, you cannot put n0. You have to put n1. So if you put n1, you get 3 by 2 h cut omega. Then you cannot put n2. You can put n3. And if you put n3, you get 7 by 2 h cut omega. So this is my ground state. This is my first excited state, and so on. Now all I have to do is to compare the energies of every graph. So basically they are asking if ground state energy in P and ground state energy in Q will be same or not. Ground state energy in Q and ground state energy in S will be same or not. Ground state energy of P and first state energy of R will be same or not. Ground state energy of R and ground state energy of Q will be same or not. So they're just asking us to compare. So let's do that. So first of all, we look for the P. For P, we know omega is given to us, which is 12, and V naught is 0. So omega is 12 and V naught is 0. And if I'm trying to find the ground state energy will not be h cut omega by 2. Ground state energy will be 3 h cut omega by 2 plus V naught. There is no V naught here, so plus 0. And omega is 12, so you get 18 h cut. If you put omega at 12, you get 18 h cut. So the ground state energy of P is 18 h cut. Okay. What about ground state energy of Q? For Q, the omega is 12 and V naught is 3 h cut. You can see omega is 12 and V naught is 3 h cut. So again, if you're trying to find the ground state energy, so it will be 3 by 2 h cut omega plus some constant is added. So V naught has to be added 3 h cut. So if you put omega as 12, you get 21 h cut. Similar thing you can do for R. For R, omega is 4 and V naught is 4 h cut. If you are finding ground state energy, you are getting 3 by 2 h cut omega plus constant. So you get 10 h cut if you put omega as 4. And they are also asking for the first energy for R. In the options, it is also there. So for first energy, you will not have 5 by 2 h cut, you will have 7 by 2 h cut and plus some constant. And if you put omega 4, you will get 18 h cut. Right. And then you can have for S omega is 14 and V naught is 0. And the ground state energy can be 3 by 2 h cut omega plus 0. If you put omega 14, you get 21 h cut. Okay. So now you can just match which of them are same and which of them are not same. If you do that, B, C, D, and will be the correct options. Okay. Someone asked that how to identify it's a half harmonic oscillator. So clearly it is given to you in the equation as well. Key for x greater than 0, you have a harmonic oscillator, but for x less than 0, you don't have a harmonic oscillator. You do have is an infinite potential. So left hand side you have infinite potential, right hand side you have a harmonic oscillator. So it's a half harmonic oscillator. For a half harmonic oscillator, 0, 2, 4, 6 states are not possible. 1, 3, 5, 7 states are possible. And that was a trick you had to use in this case. Okay. So yes, any doubt in this problem? Sir, is figure Q and R possible as it is not starting from 0? So see, this is not a diagram for a wave function. This is a diagram for a potential. You see, don't confuse this, right? Not every diagram is for wave function. Wave function should be 0 here. Potential will be 0. That is not any condition. Potential do not need to be continuous. Wave function needs to be continuous. So if I'm drawing the graph of wave function, these are the graphs of wave function, right? And we saw that in graph number 1, you have 0 at the center. At graph number 3, you have 0 at the center. So that is why I only took 1, 3. These graphs are for the potential graphs. Potential can be 0 or non-zero at the center. That does not matter. Okay. So yeah, potential need not to be continuous. Wave function needs to be continuous. Okay. Yeah, that is why all 4 are possible. Clear? Yeah, any doubt here? So a very beautiful question, and I think this is one of the most favorite questions of GATE. And this at least has been asked 2-3 times in PYQs, and also in yesterday's question also we discussed the same concept. In CSIR Net 2024 also they asked the same question and we discussed it. So basically they are giving you 2 things. One is H naught, which is a initial Hamiltonian. H naught only depends upon R. It do not depend upon theta. Okay? And then we have a perturbation. This perturbation is because of the spin orbit coupling. So H dash is depending upon L dot S. L dot S will definitely contains theta, because if you remove dot product, you get cos theta. Then basically what they are asking is, will H dash commutes with L square? And yesterday I gave you key L dot S commutes with J square, L square, S square, and J square. Okay? J, L square, S square, J square. These are the 4 things with which L dot S commutes. So yes, H dash 2 commutes with L square. So A option is correct. Right? If you remember yesterday's class, we did that. And I told you that this is going to be important for you in future as well. So yes, it comes out to be useful. L dot S do commutes with L square. H dash does not commutes with LZ or SZ. So this is going to be wrong because it only commutes with these 4 things. Clear? C option I will see. Then now let's come to the 4th option. Now they are asking about H naught. Not H dash. They are asking about this H naught. H naught is only function of R. So whenever the Hamiltonian is only a function of R, basically it has a radial symmetry, it commutes with L square, S square, LZ, and SZ. You should always remember this. This is actually the very basic. If you read the Griffiths chapter number, I think 4 in quantum mechanics in 3D, when you solve the question on hydrogen atom, and even in my lecture, I have mentioned that. Yes, it can come. It can come. These days, Jam can ask this question. Not directly, but at least Jest will definitely ask. Jam, very difficult that they will ask this. Okay. Now, L square, S square, LZ and SZ, two commutes, means you can measure all of four together if your Hamiltonian is only the function of radial symmetry, R. It is not a function of theta. So always remember this. For any wave function, for any energy or any potential which only depends upon radius or R, then your L square, S square, LZ and SZ will commute with each other, and it will also commute with the Hamiltonian. So that is why H naught is commuting with L square, S square, LZ, SZ. So D option is also correct. Okay. Yes. Now comes the C. C is a very basic thing. For L, how many degeneracy will be there? So you know that if L is 0, M can only have one value, which is 0. So 1. If L is 1, then M can have three values, -1, 0, 1. So 3. So if you take general L values, how many values your M can take? 2L plus 1. Right? If you have a L state, how many values of M are possible? 2L plus 1. Right? This is basic quantum numbers. If you have watched the basic lecture on quantum mechanics in 3D, you know this. If you haven't, watch this lecture. So if you have a L state, how many values of M are possible? 2L plus 1. Perfect. So states are 2L plus 1 possible. Now, since we are adding the electrons in the atoms, and every electron can take spin up or spin down, so degeneracy has to be multiplied by 2. So that is why I also multiply by 2. So that is why the overall degeneracy is 2 plus L plus 1. And that is exactly your option, 2 into 2L plus 1. So basically what they're asking is that for one value of L, for example, you know this. If L is 0, which basically means S state, how many electrons you can put? 2. L equals to 1 state, you have p orbital. In p orbital, how many electrons you can put? 6. Right? In d orbital, how many electrons you can put? 10. And you can try that. If I put 1 here, or if I put 0 here, I will get 2. You see 2 electrons. If I put 1 here, I will get 6 electrons. If I put 3 here, I can get 2 here. So I will get 4, 5, 5 into 2, 10. So I can put 10 electrons in D. So for any L, how many electrons you can put, or what is a degeneracy? It is 2 into 2L plus 1. So option number C is also correct. So A, C and D is correct, and B is going to be wrong. And so the correct option to this is A, C and D. Okay. Why A? Because H dash, which is L dot S, commutes with these parameters. H dash do not commutes with this. This is anyway is a general knowledge of atomic, and any Hamiltonian which is just a wave, just a function of radius, is going to commute with L square, S square, LZ, SZ. Commute basically means you can have the same eigenstates. You can measure both of them at the same time. So whenever the two parameters commute, whenever the two operators commute, they have the same eigenstates. They can be measured together. Their uncertainty product is 0. So these are some of the things you should know. Yes. Any doubt in this question? I can help any. Please let me know. Perturbation theory. Now the question number 6 is from perturbation theory. Very simple question. You just need one formula and that's all. Okay, so not every time GATE gives such kind of question, but they gave the question in 2024. So what they say is a particle of a mass m is in infinite potential of width a. So you have a well which width a, and the perturbation is given, and you can see the perturbation is only here. So perturbation is from 3a by 4 to a. So perturbation exists from 3a by 4 to a. Okay. And what is the perturbation value? The value of perturbation is also given. Then they are asking what is the first order shift in energy of the fourth energy eigenstate. So what is the wave function? So wave functions for a infinite well is given by √2a sine of n pi x by a. That's all. So since it's a fourth energy eigenstate, so you put n4 here. So you get 4 pi x. Then you have to find the perturbation. How much is a value of perturbation? You have to find the perturbation in the fourth state, and you have to find first order perturbation. So I write 1 here. So how do you calculate that? Phi 4, and then you write perturbation, and then you write phi 4 again. Okay. So how do you write this thing? In wave function approach, you write this thing as phi 4 star v dash phi 4 into dx. As I mentioned, whenever you try to go from Dirac notation to wave function notation, you can convert these symbols into integration. So that is what I have done here. So this can be written as phi 4 star, this can be written as phi 4, and this comes as such. So if this is constant, so this anyway I can take outside, because you can see this thing is a constant, right? So this thing can anyway be written outside the integration. Here you can see I have written it. And then you multiply phi 4 star and phi 4. Since phi 4 is a real number, so phi 4 star and phi 4 are the same thing. Basically, if you take the complex conjugate of a real number, nothing changes. So if you multiply this with this, you just get a squared up thing. So you get 2 by a into sine square 4 pi x by a. Take every common term outside, and then you take the integration. So now your perturbation only comes from 3a by 4 to a. So your integration should only be from 3a by 4 to a, because perturbation is 0 everywhere else, and it only exists between 3a by 4 to a. So perturbation basically means you have a normal harmonic potential well, but in this much region you have some perturbation added. So some extra potential which has been added here, right? We have done many such questions in the lectures. So if you see the lectures given to you, you will find this question to be very easy. Now you have to integrate this, and now you know how to integrate sine square theta. We use this identity, cos 2 theta equals to 1 minus 2 sine square theta. So this you can write like this, and then you can integrate this, then you can put the limits. If you put the limits, final answer you will get is h cut square by 160 ma square. So what they're asking you is answer is actually h square by n ma square, and they're asking what is n. N is 160. So the answer to this question is 160, which is true. So the answer to this question is going to be 160. And I hope this is clear. This maths you can do very simple. Just do the integration and put the limits. Everyone can do that, and you are going to get an answer 160. Okay. So yeah, if this is clear, then we will go for the last problem, which is my favorite question. Yes. The last question. And this is my most favorite problem. For all the 7 problems which were there, this is my favorite one. So they are giving you some wave function. So you have an electron in a Coulomb's field of a proton, basically hydrogen atom. So for a hydrogen atom, they are giving you a wave function. So it's a superposition wave function. So phi 1 0 0 means that n is 1, L is 0, and m is 0. Here n is 2, L is 1, and m is 0. Here n is 3, L is 2, and m is 0. Okay. E1 is the energy, E1, E2, E3 are the energy of first 3 levels. Okay. Concept number 1. In hydrogen atom, energy only depends upon n, and this we have derived in the class as well. If you see quantum mechanics in 3D lecture, you will find this out. Energy only depends upon n, and if I want to remind you the formula, this is a formula. Okay. So as long as your n is same, your energy will be same, and if your n is different, your energy will be different. Okay. So n in all the 3 states is different. So this is going to have energy E1, this is going to have energy E2, and this is going to have energy E3. Okay. Then they say a sequence of measurements is done. So they do the measurements in a sequence. So what do they do? So they do the energy. So energy is measured at the time t1. So at time t1, they measure the energy, and the outcome is E2. And then you know that what is an outcome. So it means after the measurement, my system will occupy this state. My system will occupy this state. So now my system is in phi 2 0 0. sorry, 5210. Because if I am getting the energy E2, it means before the measurement, my system was in all the three states. But once I do the measurement, I just get one of the three values. And what value I got? I got E2 value. So after the measurement, my system took which state? Second state. Now my wave function is this. My new wave function is this. My system collapsed. So in quantum mechanics, measurement can result in collapsing the system. So the wave function, which was a superposition of three states, after the measurement have just one state. And that is exactly what happens in every quantum mechanical system. Before measurement, your wave function can be in many states. But after the measurement, your wave function will always be in just one state. Or, yeah, one state. Sometimes, okay, in one state. Clear. Basically, it will just give you one value. Rather than I should say one state, I should say it will give you just one value. So you get a value E2. Then the total angular momentum is measured. Okay, we let them measure the angular momentum at time T2. And finally, energy is again measured at time T3. So we again measure the energy. What is the probability that you will find the state when you did the energy measurement again, third time? What is the probability that you will again get energy E2? Now, many people confuse this question and then they say, oh, okay. So basically we need this, and probability is given by 1 by root 3 whole square. So I know it is 1 by 3. So the probability is 1 by 3. No, it's wrong. When you did the first measurement, your system came in this state. Now you have just this state. When you do the angular momentum, okay, nothing changes. You remain in this state. And then you again, when you do the energy, you are for sure, you know that you are going to get energy E2 only. You are 100% sure, because after the first measurement, your system came in this state. Now you are not in that previous state. Now you are in this state. Then you do the angular momentum, and that does not change anything. And then you again do the energy measurement. And now if you do the energy measurement, you are for sure knows that you will get this energy only, because only thing that is possible here is 5210. So the probability in this case is 1. Okay? Probability in this case is going to be 1. Okay? But they are asking what is the value of P. So they are saying that answer is equals to P by 9. So what is the value of P? So what I will do is I will multiply by 9 and divide by 9. So it will be P by 9. So what is P? P is 9. Okay? So the value of P is 9. Because 9 by 9 will give me 1. So my probability to get E2 in the last measurement is actually 1. It is not 1 by 3 as you do here. Because after the first energy measurement, I converted my system into second state only. So when I will again do the energy measurement, I will for sure know that my particle can have only one value, which is E2. So my probability to get E2 is 110% sure ki I will get E2 only. Okay? So because first time when I did the energy measurement, I could have got this, I could have got this, I could have got this. But okay, I got this. When I got this, my wave function collapsed, and now my new wave function is this. Now this is my new wave function. Now when I will do the energy measurement on this, there is only one possibility that it will give you the energy E2. That is why the probability to get E2 is 1 and probability to get E1 or E3 is 0. Okay? So that is why the answer to this question is 1, or in this language of this question, P should be 9, so that 9 by 9 gives you 1. Okay? So that was your final question of GATE 2024. So the 7 questions were asked in GATE. All were very basic, simple problems. If you do watch the lectures, most of them you can solve. Okay? So please make sure that you watch the lectures. Right? Any doubt in today's lecture, please